Welcome to part 2 of Hands-on Arduino working with encoders. Today we're talking about encoders. Last time I mentioned that there are a number of different kinds of encoders. So here we have, for example, optical transmission encoder that can be connected up to a motor. So this one in particular has 1,000 pulses per revolution. And in this particular case, you can see that there's a connector that attaches to here, and it tells you exactly what the pins need to be. So this is a very common layout for the pins for encoders. So you have a channel B, you have 5 volt. In other words, it requires power, 5 volt, and then there's a ground over here, and then there's channel A, and there may either be something here, it says NC, no connection, or there may be an index attached to that pin. So I discussed what an index was last time, and there was a little video that showed how that worked. So this is an example of an encoder. Here is another one. So that one is an optical transmission encoder. This one is a magnetic encoder. So you have this. So it's attached to a motor. So here's where you attach the power for the motor. This one has these connections, and so there's a little toothed wheel here, and this toothed wheel is attached to the motor shaft, so when the motor turns, the toothed wheel turns. And over here we have a Hall effect sensor, and the Hall effect sensor can pick up magnetic variations. So it, as each tooth goes by this Hall effect sensor, it picks that up, and it then has additional circuitry in here that converts that signal into a nice square wave. Actually, it does the square wave in quadrature. So we talked a little bit about quadrature last time, and so that's what this is. This is a magnetic, and so often you will find these things in a attached to a motor, and it'll often have it encased in a little cover like this. So in this case, the cover isn't, in some of the cases, like for example like this is an optical encoder. You don't really want light getting in there because that kind of messes with the optics, with the lighting. In this case, the cover is not for lighting, it's for keeping dust out. Okay. Here is another example of a larger motor. This one actually has an encoder in there, optical encoder. So it's very common for an optical encoder to have 4 wires. Again, 3 for power. 1 for power, 1 for ground, and then 2 for the signals. Okay, so that's what those are. This is another one. This one also has this one has a magnetic encoder inside. You can't really see inside there though. Here is an optical a switch encoder. This uses switches. Okay, so this is sometimes referred to as a digital pot, and I actually have a shield that we're going to be using later that has a digital pot mounted. So one of the problems of these little guys when people try to use them directly is that you actually need a fairly secure physical mount to this thing, or else it will have problems. It's, if you just try to use this on a breadboard and stick those little pins in the breadboard socket, you're going to end up having trouble because the thing won't stay in there when you're trying to turn it, when you're physically trying to turn it. So it's nice having it mounted on some kind of physical breadboard, or like a actual physical circuit board to work with. Okay, this one is an optical encoder, and here you can actually see the stuff inside. And when it's running, you can actually see the LED lit. So a number of different options. Here is an encoder that has it's connected to a bunch of gears and stuff. And so you can see here's the optical disc, and so here's the emitter and detector associated with that. And so this one in particular, notice that it only has the encoder itself only has 3 wires, and it has the 2 wires for the motor. And these 3 wires then show that this is not a quadrature encoder. This is only used for unidirectional. with what we talked about last time, one directional encoding. And so that is only primarily used for counting the number of times you've gone in a certain direction, or for estimating the speed. And we'll see how to do that in a little bit. Incidentally, in case you're wondering where I got all of these, actually I think all of these I pretty much got off the internet, eBay. I think I got these off of eBay, and so you can do a search for DC motor with encoder and find some of these guys, and you may be able to get some reasonable deals. The prices fluctuate all over the place, and sometimes you'll find a nice motor like this, like I said, with an encoder that you can see through, and you know, it may have reasonable amount of torque that you can use for some robotics type project or mobile robot or something. Sometimes you'll be able to find them with gears. So this actually is a motor with a 90-degree gear attached to it, and so you may be able to find different configurations for these motors. But take a look on eBay. eBay is a great place to look. There may be other surplus stores that may have them. They're getting harder to find as people are finding these more and more useful. They're getting harder to find cheaply. So, for example, this motor, I found these big guys a while back, probably about 15 years ago. I found these guys, and at the time they were about $15 a piece. So I think they came off of a copying machine or something like that. But what happens then is now I can't even find these motors, or if I can find them, they're like $60 versus, you know, $15 when I first saw them, and they were surplus. So you may still be able to find good motors, or, you know, for larger projects and things, but that can be a challenge. So, but keep your eyes open. It's always a good idea. You may be able to find some good places local that have stuffs, like a electronic junk surplus place nearby might have stuff. But again, eBay is a good place to look for all kinds of surplus things. So if you just want to experiment with something, it's like, where do I get something with an encoder on it? Well, those are some places. Little guys like that, you can find many different locations. But again, it's a lot more complicated to use those. In terms of physically the mounting. So here they're already mounted, and so you don't have to worry about them coming loose when you turn the motor shaft, for example. We're now going to try this first experiment where we will be using polling. So if you recall what polling is, that's where we continually in the loop just keep checking to see if a signal is changing. So in this case, we're looking for A. We're going to be reading digital pin 3, and we're going to see if A changes. If A changes, then we'll increment the counter. So this is for one directional encoding or decoding. And so here we have this motor set up, and we can work with it. So this is the big motor. So we're going to first go ahead and compile this, run it. So the initial count is 0. And I'm basically displaying the new value of count every second. And so as I turn, notice it's incrementing. If I stop, it stops incrementing. And if I turn it even the other direction, it still increments because it's only counting pulses. It's not counting which direction it's going. So it works. Cool. We can get a lot of counts going with this thing. In this case, we have a fairly large counter set up. Our counter is set up to handle long, unsigned long, so that's like a lot of counts. And so I can spin this thing as much as I want, and it's never going to overflow. Or rather, it's going to take a long time before it overflows. Okay, so this is polling. Our next example is an example of using interrupts. Very basic interrupts. So again, here's the code. And again, all of these codes will be posted at a link on the YouTube site. So follow the link and you'll be able to download all of these sample codes. So you'll have them available if you want to look at them. So this uses the basic interrupts. So I call my interrupt service routine, in this case, transition. I'm using pin 3. So even though I have my my motor hooked up to both 2 and 3, I'm only actually using 3 here. In the loop, all this does is every 1 second I print out the count. So that's all that the loop is doing, is it's keeping track of 1 second. When 1 second occurs, it prints out the count value, and then it continues from there. So that's the program. So I'm going to compile it, and then after it compiles, I'm going to take a look here at the console, and I can see that it stays 0, and if I turn it, it in fact increments accordingly. It doesn't matter which direction I turn it, and I still get the it incrementing because we're only using one channel of the encoder. So this is still one directional decoding. Since it's using change interrupt, then we actually are getting 2x decoding. So this is 2x decoding using interrupts. We're now going to look at the subject of velocity estimation. Velocity is related to the speed at which something is turning. So for example, something turning at so many revolutions per minute. So for our encoder, the number of pulses that we get in a particular period of time determines or can be used to estimate the speed of the motor. So at any particular moment in time, the speed might be a little bit different from another point in time. So basically we're getting an average speed over the amount of time that we're going to be working with. So in this sketch, we're going to be displaying the number of transitions per second. So this, again, is only using one channel of our encoder, and so basically each second, 1 million microseconds, we're going to be looking at the count, and then we're going to print out the count, and then we're going to reset the count each time. So the value that is printed onto the console will be the number of pulses in that previous second. So it's pulses per second. And so that's what we're working with. Again, our interrupt service routine called transition, all it does is just increment our counter. So it's very simple. This is 2x decoding, and it's using interrupts. So let's go ahead and compile this, and we'll look at the output on our console. And so as I turn it, you can see the number changes. If I stop turning it, it goes back to 0 pulses per second. So otherwise, it computes an average number of pulses per second. So notice it doesn't matter which direction I turn it, whether forward or backwards, it is still giving me the number of pulses since the last second started. So you can see the values vary depending on how fast I turn it, and if I stop turning it, I get 0. Okay, so that's a velocity estimation. It's not giving you the actual velocity at any particular time, it's giving the average velocity over a second. So as I'm turning it, I might be accelerating or decelerating. It doesn't keep track of that. It only knows how many pulses it got in that 1 second. So this is velocity estimation. We're now going to talk about bidirectional decoding. In this case, we're going to do it using logic, using a switch case approach. So here is our code, and again, this code is available to you on the slides. So I'm not going to go through it in detail, and I actually discussed it in the previous video. So let's just run it, see it work. So this is the switch case. So here we are. We're looking at position information, And so we can see that as I turn it, it increases. As I turn it clockwise, as I turn it counterclockwise now, it decreases. Okay, and it even goes negative. Okay, so it can go positive, it can go negative. So it is really keeping track of the position. Okay, and it's actually doing the decoding. Sweet. In this sketch, we did the decoding, the bidirectional 4x decoding, using an array to do the logic for deciding whether to increment or decrement our counter. So here's the code again. This code is available to you. Here's the array that we're going to use. And so this is, again, just another approach at doing the decoding. So we're going to go ahead and compile this, and then we're going to run it. And here's the console. So again, I can go forwards, backwards, and it works flawlessly. This is the encoder for bidirectional using an array. So we've now covered all of the approaches from our last video and demonstrated them using an encoder. Now we're going to move on to talk about two new subjects. We're going to be talking about Pinchange interrupts, and we're going to talk about how to do all of this using assembly language. So the Pinchange interrupts, again, if you go back to lecture number 10, there's an explanation of how to use Pinchange interrupts. So we're going to use those here. And so up until now, the examples that we've shown have all used the standard external interrupts for Arduino on pins 2 and 3. Now we're going to use different interrupts to work with. So Pinchange interrupts. Now when it comes to Pinchange interrupts, it turns out that there is actually a library available to do encoders using Pinchange interrupts. So one method that's available, there's a library called Ada Encoder. Wow, there's even an encoder library. So it provides a way to use the encoders, works with any I/O pin, analog or digital. It's based on object-oriented programming, and it can work with either switch-based or optical or magnetic, any type of encoder. And there are tutorials available online for how to use these. I'm not going to demonstrate how to use them. Actually, there are certain advantages to using them, certain disadvantages. So the point is, I want you to understand how to do encoders. So I want you to understand what they're doing when they do the encoders, and so there's certain advantages to just using what has already been done. In this case, the library is not as simple and straightforward as a lot of other libraries. It's got some subtle things that make it kind of complex. So again, in the vein of having you understand what's going on, I'm going to lead you through how to work with Pinchange interrupts in order to do these decoding. So bidirectional 4x decoding using pin positions. So when you have an encoder connected to some channels, it's got to be connected somewhere, some I/O positions, and in general, it's not always possible to have the A and B connections connected directly to digital pins 2 and 3. It may be essential that they be attached to elsewhere. Pins 2 and 3 may be used for something else. Also, if you're going to be using more than one motor or more than one encoder, then it's just not possible to use only the internal interrupts unless you're doing one directional decoding. Okay, but in general, we want to know how to work with any particular pin. So Pinchange interrupts may be used on any analog or digital pin. So associated with each ports B, C, and D, there is a Pinchange interrupt vector. So notice you only get one vector for each port. Okay, so when an interrupt occurs, you kind of need to assess what's going on in order to determine whether an interrupt has occurred or not. So let's review real quickly the process of doing pin change interrupts. Again, you need to set the appropriate pins to be inputs. Okay, so the data direction needs to be addressed. Also, if you need input pull-ups, then you need to make sure to set them up. So for example, if you're using a rotary potentiometer, then you'll need to set up those input pull-ups. If you're using an optical encoder, you don't want to set them, okay, because that actually can mess things up. So if you need a pull-up, use it. If not, then don't. Okay. Next, you need to make sure to set up the appropriate pin change interrupt enable bit. Okay, so that would be either, depending on the port, PCIe 0, 1, or 2, depending on whether it's B, C, or D. Okay, and these bits then, there's only one bit per port, and they're in the register PCICR. Next, you need to set the appropriate pin change mask. That is, there for each of the interrupts, there is a pin that enables that interrupt. Okay, and so that is set in the PC int, and NN is either 0, 1. The number then corresponds to which interrupt you're actually working with. And so if you go back to lecture 10, there's a whole table that shows you which pin is connected to which pin change mask. So we need to make sure that that is set properly. So again, because of the fact that we have only one interrupt service routine, or only one vector per port, we need to take care of that. So I'm going to go through the code here so that you can see what's going on in this whole process. So here is the code that we will be using. So again, we're going to use a long count. So notice it's not an unsigned long. We actually want a signed value because we want to be able to go positive or negative. So again, we're going to define our time variable. I'm going to define port C val. That's going to be what I'm going to use to read port C. And I'm going to use an index to work with the array. So notice that the array and the index, we want these to be volatile because we want them to be used within the interrupt service routine. So remember, volatile variables are specified, and they're going to be used. What happens is that the interrupt service routine is not called by the main program. It's called by interrupts. And as a result, when the compiler goes through to compile, it sees that the main program never accesses the interrupt service routine, and so it tends to shut down any variables in their global variables and their use in that place if they're only used in that place. And so that's why we need to use volatile, because that the compiler won't automatically just ignore them. And so anyway, that's why we use volatile. Well, so here's my interrupt service routine. I clear the variable. I set the present state becomes the past state. Then I read in. So the state here we saw when we looked at the different transitions previously, states 0, 1, 2, and 3. We're gonna use those same states like we did when we work with the array. Okay, so port C val, I'm going to read port C, and then I'm going to mask off. I'm going to AND with this vector in order to, this binary, in order to just pick off these two bits. Okay, and so that's how I'm going to isolate that. So anyway, I'm going to call that port C val. Then I'm going to go through and check each condition. So depending on which bits are set, that will tell me what state are. So this is, I call this pin position, because the mask that you use is based on the position of the location of the pins. So in this case, we're actually using pins 3 and 4, analog pins 3 and 4. Okay, so that's on port C, and so here are the pins we use, pins 3 and 4. Okay, so these are the different possible combinations that we can get, and those each are assigned a state value. So we have the state the previous time set up, and now we have the state at the present time set up, and then we can go through and use the index to get our new index, just like we did in the previous example using the array, and then we update our counter. Okay, so notice we cleared the interrupts to begin with, then we reset the interrupts on the way out. So that's our interrupt service routine. In our setup, we basically set the data direction that we need. In this case, we're going to be using a shield that has a digital pot, and so it's going to require input pull-ups. So that's why we have this going. And then we basically do here what we did in our interrupt service routine to determine the state. So in other words, we need to set the initial state value, okay, so that we can work with it here in the index. And then I need to set the PCICR. So this sets up the interrupt register 1, interrupt vector 1, so PCInt1 vector. Okay, that enables it. And then PCInt11 and PCInt12 are associated with analog pins 3 and 4. Okay, and so this is enabling those two pins. So I set the PCICR and the PC mask 1 for, again, that's for vector 1. And so this sets us up. So now we're ready to do interrupts. Okay, we're ready to do interrupts, and they'll do pin change interrupts. Here's our loop program. It's the same loop program that basically prints out the count every second. Okay, so this is our program. It's fairly straightforward. So let's watch it work. We're now going to use the pin position approach that we just talked about. And so here's our code that we're working with. So again, we're going to use pin change interrupts. And now we're going to work with a different encoder situation. So here is our digital pot that we're working with. And in this digital pot, we need to set up pull-up resistors in order to be able to use it. So this doesn't have as many pulses per revolution as the motor did. So here we're going to actually be able to see individual pulses going on. So let's go ahead and run this program. We're going to go ahead and compile it, and then it's always good when it compiles. They're going to run, and so notice we're getting zeros coming out. And as I turn the pot, notice I turned it one way, and it gave me negative values. I can turn it the other way and get 0. And now gets values. So notice that I seem to be getting often multiples of 4, plus minus 4, minus 8, multiples of 4. And the reason we get them is because this thing has detent positions. In other words, it clicks. Each time there's a pulse, it clicks. And so the clicks generally occur, and there are 4 transitions in every click. So sometimes it'll stop just shy of a click, or just a little further than a click. Okay, so it doesn't always stop exactly perfectly all the time on the same click, but basically it clicks on a number that's a multiple of 4. Okay, so this shows that in fact we have the quadrature decoding, that it's actually doing 4x decoding. Okay, and so if we turn it very carefully, we can get it to pulse 1 at a time. There's 2, 3, 2, 1, 0. So that is pin change interrupts. Next, we're going to move on to doing the 4x bidirectional decoding using assembly language. So this is the power user version of all of this. So in our program then, remember our program, we're going to have the INO file, the .h file, and then the .s file. So here's the INO file. This is basically what we're doing. So this is the setup routine. Okay. So notice here we're going to define as unsigned long the time variables associated with this, but notice none of the other variables are defined this in here. Okay. We go through and we do the same kind of thing like we did in the previous example. And now notice here I set count equal to a number. Notice count hasn't been defined anywhere here yet. Okay. Count is defined in our H file. So here's our H file over here. So here's count. It's defined as an int 32t. Okay, and so then here's our loop program. It's the same loop program we've been using. Okay, and so notice that I have to define it this way. If I just said count equals 0, it kind of throws the compiler off. It doesn't understand 0 when you have an int 32 defined. So I actually have to specify all 32 bits that way. Okay, so this is the INO file and the H file. So here we've defined our interrupt vector. That's going to be used for our Pinchange interrupt. Okay, so this is very much like what we used in the previous example. Now we're doing things in assembly, so we have to do it a little bit different. So we have to define these extern C's. Okay, and we're going to keep track of our state in the process. Now, to actually understand what we need to do in terms of assembly, I'm going to kind of walk step by step through this. Okay, I'm not going to hold your hand because it's kind of hard to do that over the video. But anyway, it's the next best thing. So here's what the actual flow chart for what we're going to do in assembly looks like. Again, we're going to take this piece by piece, so don't get overwhelmed by what looks like the enormity of all of this. Okay, so we're actually going to do it piece by piece. So this is actually just the interrupt service routine. Okay, so we first start off and we're going to start our interrupt service routine, and we're going to save registers and then disable interrupt. So let's see how all this works. So I'm going to include AVR IO, so that gives me access to the names. Here's the file name that we're working with. Now we have the data section. Here I'm going to define the state, the count, and the past state, and then the port C. So port C is like what we had before as port C val. Okay, and so these are kind of like global variables. They're not global variables, but they're like global variables within that can be used within the assembly code. The actual global variables are the state and the count. Okay, so notice the state is a 1-byte quantity, the count is a 4-byte quantity, and so again these are globals. And then here's our interrupt service routine vector. So so notice that we have two channels that can actually cause an interrupt because of the way things are defined. In our particular case with this digital pot, we're actually on analog pins 3 and 4, and so we need to work with port C in all of this, which corresponds to PCInt1 vector. Okay, so in our block diagram or a flow chart, we're first going to save the registers that we need, and then we're going to disable interrupts. Okay, so here's what we're doing. So we're going to push R1 and R0. Then we're going to take the status register and put it into R0 and push that. Then we're going to go ahead and clear, so exclusive OR R1 with itself basically clears R1. So in general, we often assume that R1 is 0, but here we actually explicitly make it so. And then we're going to push registers 24, 25, 26, and 27. So we're going to push those so that we can save their values in case they're needed elsewhere. We don't want to lose them. Then I'm going to clear the interrupts, or I'm going to disable interrupts. So that's these first two things. We're going to save registers, and then at the end we're going to restore the registers and enable interrupts. So this is the first part of flowchart. So that part of the flowchart then proceeds this way, all the way down here. So the first thing that we're going to do is we're going to put the present value of the state into some place called state P. So we've defined a variable called state P. Okay, so I'm going to take the present value of the state. So this is entering the loop. So it's not actually the present value, it's the previous value of state. Put it into register 24, take register 24, put it into state P. So these two commands basically do this one command. Okay, now I'm going to input into register 24 pin C, and notice again pin C, when we reference it this way, this is actually its memory address, not its I/O address. So in order to use the in command, we need to use the I/O address, and so the difference is the 20 hex. So we're going to read port C, put it into register 24. We're going to AND immediate with 18. So 18, remember, is basically this binary. So the 1 is here, that's the 1, and then 8 is the high bit of this lower nibble. Okay, so we're ANDing these two together. So that is basically giving us this. And so register 24 contains that value when we AND immediate. We're going to take register 24 and put it into port C. We need to use the STS command to do that because this is memory. This is not a register. Okay, so by using that COM command, we've actually set it up to be in memory somewhere. And I don't even know where it is, but it's in there somewhere, and the compiler knows where it is. So now I call this next part branch 0 because we're now going to be working, assuming that we're working with the state equals 0. Okay, and so we start there, and so now I'm going to compare register 24 with 18. So again, with the value. If it's not equal, branch if not equal to branch 1. Okay, so that's what this is saying. Branch. So somewhere down further in the program is branch 1. Okay, it's not in this bit of code here, but it's somewhere. So if it's not equal, go to branch 1. So if it continues, then that means it must be equal. Okay, and so we're going to put into state the variable state R1. So we've already cleared R1, so essentially we're setting the state equal to 0. So this is one way of doing that. Notice you can't do a load immediate into memory. So this is the next best thing. Since we already know that R1 is 0, we do an STS to put it into the state. Okay. Now we're going to load the past value of the state into register 24. And we're going to compare that with 3. Okay. We're going to compare that with 3. That is, we want to check, is the past state equal to 3? So that's what this part of the block diagram is asking. So we set the state equals 0. Now we're wanting to check, is the past state equal to 3? If yes, we do this. If no, we do that. So we're going to compare now with 3. Branch if equal to increm, or we're going to go increment. So I'm going to call that sub code as increm. So basically, if state P is equal to 3, go to increm. So if it continues, that means it's not equal to 3. So that's the no. So we're going to load the past state into register 24 again and compare with 1. That is, we want to check to see if the past state is equal to 1. Notice here, actually, this code probably could be omitted because when we did this compare, it didn't actually change register 24. So we actually could leave this line of code out and streamline it a little bit. So we're going to compare with 1, with the value 1. That is, it's checking to see if the previous state was equal to 1. If it's equal, then we go to decrement. So that's what we're having here. So if yes, then we go to decrement. Otherwise, we go to finish. So fini here is where we go to finish. Okay, so here's the block diagram we have, and here's the assembly code that does that. Next, we move on to branch 1. From branch 1, we come down and we have a similar set of things that we're doing. We're going to read port C into register 24. This is the present value of the state. Okay, we're going to compare that value with this. Okay, so that is, we're going to compare with this binary value. Okay, if it's not equal, so this is the value for the port if the state is equal to 1. So if it's not equal to 1, we head off somewhere else to branch 2. Okay, if it is equal to 1, that means our state is equal to 1. So we're going to put the value 1 into register 24, put that value into the state. Okay, now we're going to read the past state into register 24, and here we're going to check to see if it's equal to 0. Well, one way to do that is you can actually AND a value with itself, okay, and that will check to see if the value is 0. Or you could do a compare immediate, either way. Okay, so this is one way of doing it. So sometimes you'll see tricky little things like that in assembly. So if it's 0, then it will this command branch if equal will take you to increment. Okay, so if it's 0, it'll take you to increment. If it's not 0, it'll continue on, in which case it puts the past state into register 24, and it compares with the value 2. It's going to see if the past state was 2. If it is 2, then it's going to go decrement. Otherwise, it's going to go to finish. So this is very similar to what we had in branch 0. So this is branch 1. Branch 2 is similar. So I'm not going to go into detail with what's going on. It's basically the same kind of thing. So if port C is this value, if it's all zeros, then we go to, if it's not equal to all zeros, we go to branch 3. Otherwise, we put the value of 2 into state. We check the past state to see if it's equal to 1. If it is, we increment. If it's equal to 3, we decrement. Otherwise, we head on out. That's branch 2. Branch 3 is if this value is if this is the value for port C, then we'll go to finish. If it's not, then we'll go finish. So in this case, notice that we've gone through branch 0, branch 1, branch 2, and branch 3, and in none of those cases so this is like the default value if it's none of those cases. Otherwise, we should end up going to state 3. We're checking the past states to see if it's 2. If it is, we're going to increment. If it's not, we're going to decrement, otherwise finish. So very similar, the code structure. So the code is very similar in each of these 4 branches, branches 0, 1, 2, and 3. Okay, so increment and decrement are two routines. So in each case, increment and decrement, we first copy the counter. Okay, so here's what's happening. So in each of these cases, so notice the counter is what's called count. The low byte goes into register 24. The next byte goes into register 25, 26, and 27. We do the same kind of thing in decrement. Here, notice that we're going to add immediate word to register 24. So when we do word, it's already automatically considering registers 24 and 25. And it's going to add 1. Okay, so this, in a sense, does a full 16-bit increment. Okay, so that's nice, full 16-bit increment. Now then we need to increment the upper bytes. Okay, so this is an efficient way of doing that. Then our jump to update count. We do the same thing with decrement, but instead of doing add immediate, we're doing subtract immediate. So this is a full 16-bit decrement, and then we continue to include the upper bytes this way. Okay, so this will actually keep track of the fact that if you went from 0 negative, it will actually flip all the bits from the 32-bit number. Okay, so that's important to be able to do that. So once we've done either the increment or the decrement, we go and we copy the counter. So here we're copying the values from registers 24 through 27 into the values or the places associated with count. all the various bytes. Okay, and then we go to finish. So there's a finish routine. Here's the finish routine. What do we do? In the finish routine, we enable interrupts, and then we restore the registers. So here's the enable interrupts, and then we're going to restore the registers. So that, again, we pop these in the opposite order that we push them, and then we do a return from interrupt. So this is, phew, this is the assembly code that we have for doing the 4x bidirectional decoding. We're now going to look at the assembly language program that accomplishes this. So here is our INO program. Here is our .h file, and here is our assembly language program. So here's all the code that we had. So quite a bit. Notice that in our code we have a couple things. First of all, port C, writing to port C sets the input pull-ups. And so we see that we need to do this for this particular encoder. So the encoder associated with that. So we need to make sure that's set up. The other thing I want to show here is in this particular code I've added these commands so that I show the count not only in decimal but also in binary. Okay, so I show that because I want you to see what happens, and this will be instructive. So let's go ahead and compile the program. So it compiles. It's not very large. It's nice. And so we have both the value in binary and in decimal. And so if we go ahead and turn this, we can see that it changes basically in groups of 4, roughly. Sometimes it's off by 1 or so. Now look what happens when I go negative. See how it changes actually all 32 bits? Okay, so that's important that it actually does that correctly. So we can go positive, we can go negative. So when this thing goes positive, it actually changes all the bits necessary to make it a positive number. And similarly with negative. So this code then does the decoding for us. We've gone through and we've shown decoding from a number of different kinds of encoders. We've looked at using polling, using interrupts, using assembly language, Pinchange interrupts, the whole 9 yards. We've looked at all these. So hopefully now you have the tools to be able to use encoders in your project. Good luck, and thanks for watching.